Okay, thanks. Sorry for the technical adjustments. So my name is Tom Economon. I am a founding engineer at Luminary. Along with my co-authors, Darren, Jonathan, Raghav, we're very happy to be here. This is the first time we're participating. So great to see you all and see you all in person. Like some others, we're a young company. We're pretty new. So if you'll bear with me for a couple slides, I want to tell you guys a little bit about Luminary first before we launch into the results we submitted. So we'll be primarily focusing on case 2 today. But first, a little bit about Luminary. So our goal is really to help our customers build better products faster. And so we want them to be able to iterate, do design optimization, parameter studies, et cetera, and to do it as fast as possible. So we are a startup invested in by Sutter Hill Ventures, as well as incubated. So we started in late 2019, just before the pandemic. And we all have been working hard for the last few years during that time. And we finally came out of stealth mode earlier this year in March. So it's, again, very exciting to be here. We can finally talk about what we're doing and share with everybody what we've been cooking up. So it's very exciting, and I'm very proud to be here. Today, our customers span automotive, but like some others before us, we're also aerospace folks by training, a good number of us. So we have a number of customers in aerospace and defense, as well as other verticals, industrials, and sporting goods, actually. So I don't think I need to belabor this point too much with you folks in the room, but the way traditional simulation typically goes today is the left column. It's on-prem, you're often waiting in a queue. You aren't always given flexibility in whether you're running on CPU, GPU. You may or may not have solvers that are capable of GPU computing, and you may just be waiting a long time to get things through. You also have the sort of complexity of managing a cluster, having people run it, maintain it, take care of it. And you're in an environment where you're copying files around, you have different applications for different things. It sort of ends up being a kind of a fragmented workflow. So we're trying to sort of re-envision that process. So re-envision simulation leveraging the cloud. So what we're offering is a modern software as a service web app plus API. So you'll have a Python SDK where you can access all of our components. What is this built on, and what are the key components? So one, GPU native solver is one of the primary things that we've built from scratch. Depending on where you're coming from, what resources you have available, you can see up to 100x type performance gains. I think others have been showing some really impressive numbers as well. Software as a service. So now that you've sort of uncoupled yourself from the traditional on-prem world, we can scale out or up jobs very easily by leveraging the cloud and the elasticity of the cloud. So we're not only talking about running larger cases on more GPUs, like a single case on more GPUs, but also running many cases, maybe smaller, doing databases, design iteration, et cetera, simultaneously. And I think one of the most important points is that this is all offered to our customers as one application. So it's a single one-stop shop for everything from geometry import, cleanup, meshing, solve, viz, post-processing, all in a delightful app. So you don't need to leave the Luminary system. There are a few really interesting things that enables you to do. So for example, collaboration and sharing. So instead of kind of copying files all over a traditional on-prem machine, we now make it very easy to in-browser share results. Something that I did with my colleagues actually when preparing these DrivAer results that I'm going to show in a minute. So it allows for kind of new capability like that. Also, since everything's in one place, it opens up a lot of data science and AI opportunities, which we are working on, but we don't have anything to announce yet. I'll just say that's coming. And again, everything is also available to you via a Python SDK to talk to our API, so you can upload geometries, mesh, run, and extract your results via the API. And maybe one final point before I leave the slide. Part of the SaaS thing, the software as a service thing, is that you can just come to us, bring your geometry, bring your credit card, and go. So this is no longer a license fee model that you're going to pay for what you use. Okay, enough of that. So we decided, as it's the first time we were participating, that we would focus on just one case to kind of keep it simple. So we decided to focus on scale resolving DrivAer Case 2. And what we are going to show is based on sort of state-of-the-art DDES technology that's implemented inside of Luminary. So this is DDES with shear layer adapted length scale and the vortex tilting measure for gray area mitigation. We have both SA and SST variants available, but we're going to just show SA results today. We've done quite a bit of work on two things that have come up numerous times already today. Shielding functions, so how to make sure you're not separating early or seeing things like, we'll show a little bit later near the windshield or up on the back of the car. And we've also focused quite a bit on numerics. So we are using a hybrid centered upwind scheme with some blending to control where we're introducing dissipation, so we can make sure we keep dissipation low in LAS regions. Okay, a lot of words on this slide. I'll go quickly though, just to tell you kind of how we set up and run these things. So we're focusing on the workshop provided grids. As I said, SA DDES based on the standard SA model, but we also do have QCR and other variants available. Second order finite volume, second order in time, implicit. This is ideal gas, coupled solver, so compressible. Other things are available, of course, but not being used here. Constant density, MRF, sliding meshes, porous media, and more. But that's for another day. And the approach we took for all of these results I'm going to show is as follows. So we initialized from a steady state RAND solution. We're using some non-uniform time stepping in the early, say the first few or couple thousand time steps. So starting from a larger time step, getting down to a finer time step to help wash out some of the initial transients. After that, we are using a fixed DT of 2E minus 4 and running out 20,000 total time steps, which the ramping makes it a little funny, but if you run it out to 20 with that ramping, you end up with about 6.6 seconds of physical runtime. We average over the last 3.6 seconds. I'll show this a little bit later, but we also did a time step sensitivity study, and we see low sensitivity, but other than maybe in the lift, I'll comment on that a little bit. So let's start with forces. I won't spend too much time on this. I think that the values and the deltas are pretty consistent with what most of the SRS CFD results showed in the last workshop. So I'll highlight that the drag delta is quite close to experiment. We also, like some others, see lift being lower and also the sign flipped in the deltas. In some of our time step studies, I think that the lift even drops a little bit more, approaching 0.02. So I think that lift for us was particularly sensitive. So I think there's maybe something to look into a little bit more there. So let me move on to some of the flow field comparisons with experiment. So this is a look at the CP. This has not been adjusted. I know that I guess we're adjusting to the point there at the top of the roof, but hasn't been adjusted. But the agreement here is excellent. So if you shift it just a little bit with your eyes, I think it looks quite good. If we start looking at velocity profiles, this is L1 beneath the car. This has both the 2A and 2B experiment, as well as our 2A and 2B results. So here the agreement is very excellent. You do see a slight shift down for 2B, which near the back, which mirrors sort of the experimental data dropping a little bit there. If we look at U2 underbody, so just right behind the wheels, this is where I think we're showing not only that we're matching sort of or we're capturing the effect of the front wheel deflector, but we also have, I think, quite good inboard tire wake agreement. So if my cursor picks up here, so kind of in this inner region here, we're seeing pretty good agreement with the inboard, which I know has been hard to capture in CFD. And just one or two more, I know I'm going a little bit quickly here. So if you take the V3 position, so right behind the car, we're also seeing good agreement here. We were very happy that we're not seeing excessive separation right above the back of the car, right above the lid. Like others, we have sort of this deficit mismatch, but I think that we're kind of agreeing that that's not a surprise, but otherwise very good match. And then the last one, if you go to V5, this was the late edition. I actually just added it before presentation because it's come up so much. We also see this discrepancy in the CFD results as well. Okay, so a few more slides just to focus on things that aren't in the submission. And this is, I guess, the HPC section. So I want to highlight a little bit about performance just in one go. So again, we're using the workshop provided grid. So it's about 160 million cells with SA-DDES and running out 6.6 seconds of physical time, with the caveat there's some ramping. So what we submitted to the workshop was the following. So if you run this case on 48 A100s, we can complete it in 93 minutes. That's the full run. So this baseline performance is roughly what you would get today in our app. If you get on, click run a simulation, we have A100s there ready to go, and this is roughly approximate to what you would see today. Now, we did also spend some time looking at what our performance would be on H100. So these are coming, most of the cloud providers are making them available. This is something we're working on at Luminary that is coming soon. So sort of in the lab, we went ahead and ran this case, did some performance tuning, and we were able to run it on 64 H100s in 44 minutes. So I want to emphasize that this type of large transient case is no longer even hours. We're running these things in minutes. And if you allow me to just dream a little bit, bear with me, there's another generation of GPUs coming, Blackwell, which we do expect is maybe another 2x improvement. Along with some other performance optimizations, I should say these are double precision results. So if we move to single precision, do a little bit further work, we could be talking about turning around full DDES runs in 15 to 20 minutes. So, I mean, you can imagine the type of, iteration you could do if not only the turnaround time for one is that fast, but then you can elastically scale out in the cloud and run tens, hundreds of these simultaneously. So I think we're talking about sort of game-changing performance here, as others have noted. A couple caveats. I'll let you guys read later. I already said this, but this is for essentially the full 2A run. So the same configuration I showed with the 20,000 time steps and 3 inner iterations per time step. Okay, so we did do a couple other sensitivity studies that I wanted to share with you. I think that a couple interesting things came out. We dropped the time step to 1E minus 4, and we actually saw very similar results in terms of the profiles. As noted, we did see some changes. I think the lift is the most sensitive in terms of coefficients, so that dropped closer to 0.02. But otherwise, drag was very similar, which I know others showed that with time step refinement earlier, the drag was changing quite a bit. For us, it didn't. So that's, there's maybe more to investigate here. But in terms of profiles, I wanted to show a couple of them again. So this is our results for both the 2E minus 4, 1E minus 4, compared with the experiment. So minor changes, mostly sort of, at the back in the wake. For the cut U2 right behind the tires, we see maybe it's a little more crisp in the 1E minus 4 run, but otherwise very, very similar. And if you look again at V3, so right behind the vehicle, very similar other than, this area right behind the body where we know that, there's been some discrepancy, but, there's not much change in terms of the profile coming off the top of the trunk. So one other thing we wanted to look at while we were developing this set of results, as others have noted, the shielding function is very important for capturing what's going on in terms of separation. So we did a number of things and played around quite a bit to understand how the shielding function was impacting the results. And like others, we do see right along the center line on the top, we are basically attached. But if you go a little bit off the center, it's maybe hard to pick up here, but there are small recirculation regions here just off the center. So this is, I think, something other folks pointed out earlier. So we also found that if we messed around a little bit with the turbulence model, say use the QCR variant or try different things, that this area is very sensitive. And so important to spend extra effort on the shielding function to make sure that area is not separating. So I did highlight here just to pull the R3 profile just to share what it looks like. You can see it's very close. It wants to separate, I think. So this is definitely an area for future investment. I think if the community can keep focusing on shielding functions, I think that's a very high impact area. So, okay, that's pretty much all I had. I want to stop here. I'll take any questions. Feel free to grab me. I couldn't explain too much about Luminary or share a lot. I know there's a lot to share that I'd like to share, but I don't have time for. So grab me and we can talk, or alternatively contact Peter, my colleague, and you can get more information from him. So thank you.